Recording, share the screen. All right, so go over here. Okay, so we're going to normalize our data. Hit mark down here. Hit run. Okay, so what I'm going to do right now is just play with tensors a little bit. Okay, and the goal of this is kind of to see, kind of to what we had done before at the beginning of the semester with playing with tensors, but now for an actual application of this. Okay, so the idea is we're going to normalize the data. There's several ways that you could do this. But one way that we're going to do this is just for all, we have basically 50,000 images, right? And they are RGB. So all we want to do is we want to maintain the channels separate, right? So we're going to have the R's, the G's, and the B's, and they're not going to be mixed. And basically for every image in, let's say an R channel, we have an image that is 32 by 32. So we want to take each of those pixels and modify it based on some value. All right. And the value is just going to be the average of all the pixels in all the 50,000 images, but for each individual channel, if that makes sense. Okay, so that's the goal. So how do we achieve something like that? Well, the first thing we need is we need to take all the images and put them together in a tensor so that we can do this efficiently. All right, so I'm going to let's create a list, image list. Image list. Okay, so we're going to iterate. We're going to do a list comprehension. So for img underscore t dash in tensor. And so this is going to be, yeah, the data needs to already be tensors, right? So we're going to need to use this data set, right? Because it's not images anymore, pill images, but they are now torch tensors. So we're going to go ahead and do for img, this underscore just means that we're ignoring the label. We could also just do label. We're just not going to use it. So for image t label in tensor underscore CIFAR10, okay? So what do? We're going to process and add those in here. So in this list, we just want image t. So we're basically creating a list of all the images as tensors in here so that we can process this. Now we're going to take this list and create a torch tensor. So we're going to use the stack function. So I'm going to do imgs equal torch dot stack, and we're going to stack img's list. Okay, if we look at one of these images, actually, let's do that. So let's do img list 7, let's say, dot shape. It's not the oh, did I not run this? All right, so run it. Okay. All right, finished. Now let's run this one just to get a feel for the shape. The shape is 3 by 32 by 32, right? So we're going to stack these along a dimension. So we need to specify along which dimension this needs to be. So let's just do dim equal, and let's say that it's going to be along dimension 3. So if we do that, it's not the, oh, IMG, yeah, sorry. Okay, and now print, we can actually now treat IMGs as a tensor, right? So we can just do IMGs dot shape. And if you look closely, now we have 4 dimensions, all right? So we stack them across that 4th dimension, which is 3. Does that make sense? And created now a torch tensor that is 3 by 32 by 32 by 50,000. Why 50,000? Because there's 50,000 images, right? Got it? These are the things that are kind of complex in Torch, but they can also be very useful sometimes because we did this really quickly, right? And now we can process all 50,000 samples all at once in this Torch tensor. Any questions? It should, yes, exactly. So now we have a torch tensor, 3 by 32 by 32 by 50,000. Now let's say that I ask you the following question. Create a vector that is of size 3. So let's say A, comma, B, comma, C. And this is probably the best way of understanding this, right? So I'm just laying out where we're going. Oh, actually, even better. RGB, more intuitive, right? RGB. And what I want is, think of it this way. My torch tensor includes all 50,000 images, where each is 32 by 32 by 3, yeah? And the 3 is the RGB. But I just want you to take this tensor, IMGs, of this size, and I just want you to produce one vector, a tensor also, with just 3 values. So I want one value for all the R's, one value for all the B's, and one value for all the R's, one value for all the G's, one value for all the B's. And what is that value going to be? The average. So for instance, there's 50,000 red channels, correct? Of size 32 by 32. So what would you do? You would take the 32 and 32 average, and then that average across all 50,000, and you give me one value. Does that make sense? There's lots of ways that you can do this. Just stack, take an image, 32 by 32, make it into 1024, and stack all 50,000 and create a vector that is 1024 times 50,000, and then average all those values. However you want to do it, average, and give me one value. Do you guys see what I'm saying? Okay, so how do we do that efficiently in basically like one line, well, 2 lines of code in Torch? So that can be pretty challenging, right? But you have at least an intuition. I don't expect you guys to solve this. Like, I'm not going to give you a pop quiz or anything like that. Unless you want a pop quiz. You want a pop quiz? I'm just kidding. So how do we do this efficiently, right? But you already have a certain intuition from when we did this at the beginning of the semester, right? And that's the power of PyTorch or tensors, etc. So let's go ahead and try and see how we could do this, right? So let's add a few new cells in here. This is what we want, right? One for R, one for G, and one for B, and then we're going to use these. And right now, I'm just saying the means, right? The average. Okay, so PyTorch has a built-in function. All PyTorch tensors have a built-in function called a view. So the big tensor right now is IMGs. Okay, so from IMGs, we're gonna do dot view, right? And we're gonna create a new view. So that we're gonna name this view let's name it view means. Okay, view means. So what I need first is I just need to maintain the channels separate, but I can combine everything else into one gigantic vector, right? So how would you do that in Torch? You can just do something like this. We did this, I think, with reshape before in some of the examples. I believe we did reshape in NumPy, and it's similar. The dimension is 3 by 32 by 32 by 50,000, right? So we could do 3, comma, minus 1. Do you see that? What does minus 1 do? What did minus 1 do with the NumPys? Figure out what that dimension should be. Take whatever's there, don't lose any data, and just calculate the number yourself. So what is happening here is it's saying RGB, so it takes R, imagine. So R has 32 by 32 by 50,000. So then it does 32 by 32 is 1,024, and then times 50,000. And whatever that large number is, that's the vector that it computes. The data is there, but it is now just one single vector. And that way we can retain what is R separate from what is G, separate from what is B. Does that make sense, guys? Right? So let's go ahead. That should be enough. Let's do the print the shape to get an idea, a feel for it. So I'm going to do view means dot shape. Hit run, and there you go. Do you guys see that? So now I've created a tensor that is 3 by whatever that gigantic number is. I think this is 51 million. Think about that. That's 51 million features. That's a lot, right? You should be concerned about this neural network because it's going to be very big. Okay, got it? All right. Anyway, so we've done this. So now we can just calculate the means out of this one. So we can just say view means equal to view means. Remember, because these are torch tensors, they have built-in functions such as mean. And we need to specify a dimension across which it will calculate the means. So which one would you say? Yes, sir. Good. Nice. Good job. Otherwise, you would have ended up with a vector that is of 52,200,000, or sorry, 51,200,000 or something. And that's not what you want. Instead, you want a vector of size. Great, exactly. All right. So now let's go ahead and calculate this and print it out. Oh, print it. View means dot shape. Hit run. So you can see it's size 3. We can actually view it. View means. And we have calculated the average of all 3. This is the power of using tensor operations, okay? Very powerful things that you can do with it, super efficient and super quickly. But as I said before, I don't expect you guys to be able to do this off the top of your head. Instead, probably my recommendation is work out by hand with small data sets, make sure it works, and then apply it to the big one. You know, that's probably the best approach. All right, so since we calculated a mean for the formula that we're going to use, we're also going to need a standard deviation. So we're going to repeat this process. So now I'm going to grab this one. Images hasn't changed, so I can just use that one. I'm going to change this to standard deviation. Okay. I'm going to change this to standard deviation. Okay. That should give us a new view, right? With kind of the same idea. Hit run, right? It's got the appropriate shape. And now let's calculate the standard deviation. So we can just copy this one. Okay, this will be view standard deviation. Okay, and let's change this function to standard for the standard deviation. Okay, and the dimension remains the same, and that should do it. Or not. Oh yeah, this one, yeah, yep. Thank you. Okay, try it again. Okay. There we go, it's size 3. Then we could copy view standard deviation. And now we should have also a vector with 3 values in it, and there we go. You see that? That is the power of tensor operations. Definitely, I strongly recommend that on your own, you keep cultivating, if you will, that skill, because it's very necessary in today's world. If we ever move to, let's say, quantum computers, let's say, right? It's just an example. Then it would be something else that you have to become really good at. But I do believe linear algebra will be a part of that. Okay. More dimensions. All right. So anyway, this is very useful. All right. So that's kind of just doing that as kind of a exercise. Now let's get back to building the data set and training our model. So now we're going to actually create the data sets that we're going to use to train our model. To try to train, I'm going to get rid of this one because I don't need it anymore. I'm going to create 2 data sets, put everything together and these are the ones we are actually going to use. So let's call this transform. And then CIFAR10 train. Okay. So I'm going to call data sets dot CIFAR10. And now data path, it's going to be data path, comma, train equal true, download equal false. And now we're going to use that transforms example that we learned about, but we're gonna apply several transformations actually. So we're gonna do transform equal. It'll be equal to transforms dot compose with a capital C. So we open this one as well. And in compose, we're going to provide in a list the elements that we want in there. So for instance, we're going to say transforms dot to tensor. comma, transforms dot normalize. Does this make sense, guys? Any questions? So basically, it's like you can create a pipeline of things. Okay, so the image, when you use transforms.compose, it's going to take the image, run it to tensor, make it a tensor, then normalize it, and then you could do more operations if you wanted to. That's why you have this option of creating a list. Got it? Now normalize, the normalize operation that I selected, there are many, I just selected this one. The idea here is it takes a pixel and it's going to take that return. So it's going to take a pixel and do something like this. It's going to take minus the mean divided by the standard deviation. Does that make sense? Now we already have these values, right? We calculated them previously. The only thing is we just need to make sure that they're applied to R, G, or B. Okay, but basically that's the operation that we are doing to normalize the pixels. We take whatever pixel is there minus the mean divided by the standard deviation, and that's the new value of that pixel. The way that normalize works is exactly like that. So all we need to do is give it the two vectors that we created, and it'll work. So then we give it view means comma, by default it'll work like this, and view standard deviation. Got it? Any questions? That's just a specific way that normalize works. So let's go ahead and run it. Oh, thanks. Yep. All right, so please go ahead and run this one. All right, no errors. So now let's go ahead and run the other one. So we can just copy this code basically, and let's just modify it. So this one will be for the test set. So transform CIFAR10 test. Data set CIFAR10 data path. Train will be false here because we want the test set. Download will be false. Transform will be equal to transforms.compose. We're going to do transforms.tensor, transforms normalize, and so on. Now, if you notice, we're using the means and the standard deviations from the train set for the test set, and that's perfectly fine. If you're confused by that, just think if you were in a competition, you would never have access to the test set, but you can assume that both train and test set came from the same population. So that should be fine. Got it? Any questions? All right, so go ahead and run this one. Okay, seems to be working. You notice basically the only difference between the two is the train is true or false. All right, you know already how to check. I recommend that you print the statistics of it so that one has 50,000, the other one should have 10,000. All right, so now that we've completed this part, let's add a few more cells. Okay, so the next step is we're going to build the data set. Now, we're going to build the data set, and then we're going to build the data loader. Okay, so hit run here. So, what do we need? Oh yeah, I remember now. So the data sets, the way the data loader expects the data sets, it needs an image of tuples. We currently don't have an image, a list of tuples. That's what I meant. So we need a list of tuples, okay? That's what data loader is expecting. So we just have to modify this a little bit. So we can use a list comprehension and create CIFAR train and CIFAR test. Okay. So we create a list comprehension. So let's do for IMG, comma, label in transformed CIFAR10 train. Okay, so for IMG label and transform CIFAR10 train, and now we take those and make them into tuples. So it's going to be IMG, which is a tensor, and label, which should be just an integer. Got it? That's basically all we're doing. I'm going to repeat this for CIFAR10 or CIFAR test. Only I'm going to change the name here to test. All right, there we go. So I have now converted my data, completed the data wrangling almost, right? I have the data as a list of tuples, where each tuple contains a tensor image and its corresponding label. Let's go ahead and run that. All right, let's give it a minute. The next step will be to create the data loader, okay, which you guys are familiar with already. You know it's a module, so let's just add in here data loader. I hit cell, mark down, okay, data loader. Now for this, we'll probably need some libraries. I don't remember if I added these. They may already be in Torch. I think they're already in Torch. All right, so then let's just add our data into the data loader. Let's go over here and we're going to say train underscore loader. And we're going to assign to it. So we're going to say torch dot utils dot data loader. Okay. And we're going to provide as an input to this CIFAR train. So we're going to do CIFAR underscore train. Got it? Now, what else would we do in data loader? What were the other parameters? Batch size. Right? So what batch size should we use here? 32. You're going to have to play with this parameter, actually. So this kind of thing, you should hard code as a parameter at the top and call it batch size. So that, because you don't know, RAM may be an issue, maybe too slow, you know, all kinds of issues. What else? What was the other parameter? Shuffle. This is important, okay? We're going to set it to true. What does shuffle do? Every epoch, we grab the data set, randomize it, and then extract batches of 32 and train the model. Next iteration or next epoch, shuffle the data randomly again, and then train the model. And we do this for as many epochs as we have. Okay, guys? Got it? Any questions? All right, so that should be it, hopefully. And our data wrangling, at least for the train set, is now complete. And this is so common in deep learning, and that's why it's got a term. Okay, it's so much work. All right, now that we've done this, we're ready, right? So now it gets exciting because now we're going to build our deep learning model. So we're very close, actually, to running it. What are the things that we need? Well, one thing we need is what? The architecture. Remember that? So we're going to build some architectures here. Okay. So markdown. Okay. Now remember, this is the part that will be a homework assignment. It's an easy homework assignment, okay? Very easy. The results are gonna be what, you know, whatever you get with my approach, with the approach I'm doing. I just want to show you another way of doing this, but I want you guys to change these into the object-oriented approach that we did for the regression problems, all right? So remember, you had a class where you had an init, and then you also had a forward function. You need to write it like that. Get into the habit of that. So that will be your homework. But for now, I'm just going to do it like this. So I'm going to build two architectures. One is a multi-layer perceptron, and the other one is a deep learning, neural net. So let's just start right now with the MLP. It's a neural net, but it's not deep learning, right? Deep learning would mean what? More neurons, which means more weights, which means more parameters, which means more RAM. You need a more strain on the resources of your computer. So let's just do the most basic neural net. Call it model MLP. NN is a module. We don't have this one, right? So let's define it. We've used it before. We just don't have it here. So let's add it. This is it's pretty much what we built. That's the beauty of regression, right? Is that when you apply classification, you kind of already know how to do it. It's just a few tweaks here and there. So we're going to do import torch dot optim as optim. If you remember, this was for the learning stochastic gradient descent and all of those. And then also import torch dot nn as nn. All right, so our neural net module that we would use to initialize our own classes would come from here. So hit run, and now we have it available. So now we can use it here. Now notice I'm taking a different approach, but you should convert this to the object-oriented approach. Okay, so we're going to use nn.sequential. This is a similar approach to what, if you guys have heard of something called Keras, probably if you've had a machine learning class before, that's something you used in the past, Keras. Keras actually tried to mimic, this approach from PyTorch. They copy each other, but it's similar. So this is sequential, which allows you to lay out the architecture of your neural network. So now we're going to set up the layers. So NN linear. which will be, I'm just going to write dimension, comma, followed by NN dot tan H, which is an activation function, followed by NN dot linear dimension, comma. Oops. Yeah. So what does this look like? So this is a neural network. The multi-layer perceptron has how many layers? 3. An input layer, a hidden layer, and an output layer. What do we know about what we're doing? How many classes do we have? Classes? 10 classes, right? So we want a neural network that predicts. Before, we only predicted one thing, right? 72, 75, 76. But now we want to predict 10 classes. So how do we do this? It's a very good question, right? So how do we do it? So the standard approach is that we predict a number of neurons equal to the number of classes that we are trying to do. Okay? Let me bring out the whiteboard for this. So this is called architecture because literally you have to think about this. This architecture that you're building is pretty important. And this is where something like a CNN will have even more complex architecture, right? So we really are becoming architects of neural networks, okay? So let's analyze this one. Okay. So I'm going to switch to the whiteboard. We're going to think about this problem and how it should work. Okay, so there's the whiteboard. All right, so it's an MLP, right? We're starting with a multi-layer perceptron. And it's got an input layer, got an output layer, and it's got a hidden layer, just one hidden layer. Okay? So what do we know? In the past, when we did regression, this was only one neuron because it produced 72, 33, 55, a million, 0.05, whatever it was. But now in classification, this is a little bit different. If it's binary, which means there's only 2 classes, there's a way that you can just have one neuron. So there's like, you can do it in 2 ways. If it's binary, let's say it's just cat or dog. So you can do one neuron where the neuron produces either 0 or 1. So that's your 2 classes. Or you can do 2 neurons where the possibilities are 1, 0 or 0, 1. And that's the 2 classes. So we use this representation or that representation, but that's for the binary problem. But we don't have a binary problem. We have a 10 classes. So then for this one, we can't use this approach. We have to use this approach, right? And so all we have to do is extend this to 10 classes. This is called one-hot encoding. And so we're going to do here I'm going to erase. Okay. Okay. So we've got, for some reason, the hidden layer went away. Okay, so here we know this one for sure. 4, 5, 6, 7, let's say 10 neurons. Okay. So what that means is when we train our model, we have an image and we're going to know it's 3. That's the label. Let's say that's a cat. But we're going to want it to be 1-hot encoded. So that means this should be, if this is, it starts at 1. So this is, the first one is 1, so that's 0. The second one is 2, so that's 0. The third one is 3, so that's a 1. And then the rest are zeros. Do you see that? This is called 1-hot encoding. You take a label that's like this, and you convert it into a vector of 10, where all are 0 except for the one that corresponds to the index, basically. Okay? Yeah, go ahead, please. That's a good question. So the real data, the labels, look exactly like this because you only have a 3. So you mark this one as 1 and the rest at 0. That's the label data. So that is to say, I'm going to switch colors here. That is to say that there's going to, every time we give it an image, right? We have an image and it's like a cat. All right, so it's a cat. So the image goes into the neural network. And what does the neural network do? It produces this vector, correct? And what do we do with that vector and the optimization? We compare it to the real vector. So the real vector would look for a 3, like that. All are 0, and that's a 1, because we can do that. But what does this look like is your question, right? This will not be exactly 0s and 1s. It'll be, as you say, 0.03, 0.02, and for this class, hopefully 0.7. So it's the majority, it needs to learn. So the model should learn to produce, this is a 1 and all of these are 0s for this example. That is the goal of it. But it may not produce it exactly as this, but you want it to be as close as possible to it. This one would look like this in the inner workings of the architecture. Does that make sense? Yeah. Any other questions? So we need to build, so that's the important question there is, we need to build an architecture that has everything necessary to build this. Will it build it based on the data? It depends. But the more it builds it like this correctly, the better your model. So we need to do steps in here for it to be as close as possible to this. Okay, that's really important. Now, we use several built-in functions. So even though this is what's happening under the hood, we can use functions where we just give it the 3 and it'll convert it to the 1-hot encoding version of it. So we don't actually have to do it. We used to have to do this in the past, but a lot of that has been abstracted. But I want you to understand that that's what actually happens, let's say, under the hood. Okay, so if you had to do it from scratch, you would have to do it like that. We just take advantage of what we have today, and we can just choose a function where we just give it 3, and it makes it into that. Is this clear, guys? All right. So we need to build the architecture. We know that this architecture has one set of neurons, this one, right? And that's a 10. But we also need to specify other things about the architecture, right? Like how many neurons do we have in the input layer, and how many do we have in the hidden layer? So that's the input layer is something else that we should know, right? So how many neurons do we have in the input? You should be able to answer this question at this point. Three? Not three. What are you giving to this model? Think about it. Think about it. The image, right? Okay. What is the size of the image? 32 by 32. Are we just giving it that? What else are we giving it? RGB. So we are actually giving it a Rubik's Cube, right? Think of it as a Rubik's Cube. When it's something like RGB, we're giving a Rubik's Cube to the network. But we've only learned how to give it rectangles, right? Or vectors, one-dimensional. We have not learned how to give it Rubik's Cubes. Can we give it Rubik's Cubes? Sure. Do you know how to do Rubik's Cubes yet? Not yet. So what do we know how to do? We know how to give it not Rubik's Cubes, but vectors. I call this, but I don't call it. I mean, I saw it somewhere and I found it very funny. We spaghettify this. Spaghettify, like a person goes into a black hole and they get spaghettified, right? So it's the same idea. So how do we spaghettify a cube? Reshape, right? So basically, we can take the R, grab that, then that, and so on. And then we grab the G, grab that, and then we grab the B. Do you see that? That's spaghettifying and creating a vector. Now, did we lose any information? No. You as a human, you can understand these three images together, but if you look this, it probably won't make sense to you. Do you think that matters to a computer, a neural network? Probably not. I mean, it doesn't know anything, so it's learning. Either way, it's going to find a pattern, probably. All right, so anyway, that's what's happening here. So we don't lose the data. So in the beginning of the class, I asked you, if you take a cube that is 32 by 32 by 3 and you spaghettify it or make it into a vector, what's the size? Oh, what is the size of 32 by 32, actually? I think that's what we... 1024. And then times 3. Okay. So a cube of image RGB, if we stretch it into a vector, becomes 3072. That's one full image given to the neural network without losing any information. So then you have that information now. So tell me, what is the size of input to the neural network? 3072. Good. So remember, we only specify the size of one image. And then the batch size or however many images we give doesn't matter. That's something that PyTorch, TensorFlow, they all handle. They can take one image or 1,000 images. They don't care. Okay? But this is important. We define that this is 3072. We know this is 10. So what about the hidden layer? What size? How many neurons do you want here? Is there a theory or something? No, it's experimental. Sometimes people say funnel it. So less. Keep in mind, if you say 1,000 here, that's a lot of weights. So start on the lower side and see how, because just wait. You'll see what happens. So let's go with 200. Why 200? I don't know. Try it. Start there. That may be too much, actually. All right, so let's go ahead and do this. Did you guys understand? So that's the theoretical framework, if you will. Now let's code this up. So we're gonna switch back. This is recording, right? So we're gonna share the screen. Share. Okay. So now, what is this dimension? This value. Yep, very good. What is this value? 10. And what is this value? What is this value? Very good. Now, what else do we do? So for this to be a neural network, it has to have these hidden layers and also the activation functions. Without the activation functions, this is actually still a linear model. And it won't have the power, regardless of how many layers you put in there. So what does an activation function do? We're actually going to see an example of this one today. But basically, it's going to take the outputs and transform them. So what do I mean by that? It means that the values that come out of this layer here would be a certain number of values, but now we're going to run them through a function. And so that additional step changes these values to another set of values. Do you see that? That's it. That's what an activation function is. Okay. So let's say that the value that comes out of this is 30. But then that 30 would go into a function, let's say like tan h. So that 30 would go in there, and this would become 0.5. Do you see that? That's what happens with an activation function. It'll apply it to all the 200 neurons, okay, and modify them. As it turns out, and this kind of relates back to your question that you had, here, to make this look more like this, we're actually going to apply a type of function here called the softmax. That's a new thing that classifiers have, and I'll show you how that works. But they're kind of related. Both the tanh and the activation functions and softmax have a similar behavior. It just depends on what the function is. Okay. So let's go ahead and add that activation function. So let's go in here. Go to this screen. So now we know that after it comes out of 200, those 200 go through tanh and get modified. And then those 200 will go into this last bit, which is going to map into the 10 classes. Okay. And that's your neural network. However, we're going to add one more thing, which is another type of activation called a softmax. And we're going to say that the softmax is applied on dimension 1. Why? Because remember, the tensors that go into here are batch size by whatever the dimension is. So we don't want to do this across the batches, let's say 32, but across each individual value. Okay? All right, so what is softmax? Let's do an example of that. This is not part of the architecture. This is just to illustrate how it works. What is softmax? Okay. So softmax is very interesting. So the best way to probably understand this is through an example, okay? So softmax is an equation. Softmax is literally an equation. Let's see if we're gonna take let's do this in parts probably. All right, so let's think about this. Softmax, let's say we have a vector. Let's start there. We have a vector X. And it's like, obviously because we're going to use torch, so we're going to convert it into a torch tensor. Initially, it's a list. It's got 1.0, comma, 2.0, comma, 4.0, 3.0. Okay, there's 3 values in there. Do these values look like, so if we look at this, this is a 1, a 4, and a 3. So obviously this is the biggest one, right? So if this is a one hot encoded machine learning problem, and the class is here, out of 3 classes is class 2, then this would look like, correct? That's class 2, labeled integer 2, gets 1 hot encoded into that. But we've got this vector. That vector does not really look like this one, right? It doesn't. For one, this one adds up to 1. This does not add up to 1. Now, is this the majority one? Yes. So that matches this one, but it does not look like that one. What if there was a way that we could take, let's imagine that this is what comes out of the neural net. Will it work sometimes? Yeah, maybe. But it's not exactly in the ranges of the other one, right? What if we could take an additional step to make it look more like this? Do you guys see where I'm going with this? It's kind of what you were asking, right? So that machinery can be achieved through softmax. Okay, so let's see how that would work. Hit run. Okay, so we've got our X. Hit run. Okay, so what else do we do? Let's take X and let's do e to the X, right? So we're gonna do X equal torch dot exponential of X. And let's print X. Okay, so that's what we just did. We just did that. And now we're going to divide these by the sum of these 3. So how do we do that? We can do X is going to be X divided by the sum. Well, actually, let me do X dot sum maybe. That works. X. What do you, yeah, what do you think? How did I know to do that? I mean, there's an equation for it. Okay, and it's called the softmax. But if you apply the softmax, what is the effective thing that we did? We transform these into this, right? So if I do X dot sum, guess what it adds up to? 1. This one also adds up to 1. So they have kind of, they're more similar now. We are forcing the neural network to now produce, because the neural network could effectively produce something like this initially. And we don't want that randomly for it to produce things like that. Instead, from the very get-go, we want it to produce things more like this. Why? Because if you look, This is 0.03. That's pretty close to 0. This is 0.70, and this is 0.25. We would want a model where this is 0.03, this is 0.02, and then this is 0.95, right? That's kind of what we would want. If you think about it, what does that ultimately simulate? It simulates probabilities. If you think about it, for a 3-class problem, we're saying here, what? If this is class 1, this is class 2, and this is class 3, we're almost saying there's a 0.03 or there's a 0.3% probability that is class 1. There's a 0.70 probability it's class 2, and there's a 0.259 probability is class 3. We ascribe to it not just the class that we're going to get, which is 2, but also that it's 2 with a probability of 0.70 or a 70% probability. Do you guys see that? So that's why you want it to add up to 1, because when we look at distributions and things, like when you took your statistics class, the Gaussian, etc., the area under the curve adds up to 1. Does that make sense? So we make it more probabilistic. We additionally make it more mechanically so that it produces something that looks like this. This is nice. We have 2 things in our prediction. When we did regression, did we have this? Unfortunately, we had what? Just a neuron that would say 72 or 32 Celsius or Fahrenheit. But wouldn't it be nice if we had been able to say, I think it's going to be 32 with a probability of 0.70, or it's going to be 55 with a probability of 20 or 0.25. Do you see that? Regression does not, as we saw it, does not have what classification has. Do you guys understand? This ability. Now, can we make regression have that? Yes. And that is actually really nice work called, I think it's called mixture density networks. And mixture density networks have that property. You can assume different distributions, and then you can predict what? Ranges. So basically the network now, let's switch over to the whiteboard. This is an advanced topic, not for this class, obviously, but this would be, like another grad level class, but basically a distribution. So what I'm saying is, if we go over here, the classification problem with softmax automatically gives you that, but it gives you what would it be? 27, right? So does it give you this? No, it doesn't actually give you that. But it gives you this. This is what the neural net predicts. And then what do you have to do? Do an argmax. And what the argmax does is selects the index of the highest value. So if the index is 0, 1, and 2, it's going to select this index, which is 1, which should map to class 2. Do you see that? So effectively, you get this one. You get that it is that vector class 2, but with a probability of 0.70. When we did regression, we would only get 32, 32.5. But mixture density networks, MDNs, are a way to get this. So then what you get is, assuming a Gaussian distribution, it can give you basically, sure, 70, or, well, it gives you the value that it is with the probability associated with it. So something like that. So it says, oh, this is the value, so then that's the probability. Okay, from like your stats class. So we can make a neural net That's the amazing thing about neural nets. They pretty much, they're universal function approximators. They can do, in theory, anything, right? And so you can then get 32 with a 70% probability or so. Got it? But but the regression models we saw were not able to do that. We would have to build other architectures called mixture density networks. All right, as I said, this is a much more advanced topic in another class. However, I will give you the paper so that you can, if you have an interest in this, you can take a look. So that's a paper by Bishop, who I believe is the author of that famous Bishop book that you may have seen already, probably. These are called mixture density networks. I believe this one, yeah, Bishop, 1994. And that's the paper. So this paper takes regression, basically, as you can see, I think they have a nice graph in here somewhere. Right, so you can see it's a neural network, but now it builds distributions. It may not be here, actually. I thought I saw it here, but I guess that graph is not here. Anyway, this is the technique to get that idea, all right? So if you want probabilities associated with regressions, which you might, right? Because in decision-making, should you buy that stock at $1,000 a share? Well, no. If the wording would be, the model says buy that stock at $950 a share. Okay, but what's the probability of that? And if it says, well, with a probability of 40% versus a probability of 98%, there's a big difference, right? Both models might indicate $950 a share, but having that additional component might be a good thing. All right, so anyway, that's what mixture density networks give you. Without them, right now, all you get is buy it at $950 a share and trust us, okay? Anyway, that's, in regression, you need a lot of work to get to that piece of information, but in classification, you already have it built in, all right? So that's really great. Okay, guys? Did you understand softmax? Are there any questions on that one? It's a really important concept. There will be lots of questions on the exam about it, so. No questions? All right, great, cool. All right, so since softmax is done, then our architecture is done, right? So now we can proceed to train our model. So let's go ahead. We have about 10 minutes. Did we run build data set? I don't remember. Did I? Okay. So you have all the pieces now, and what remains is the training process, which is exactly what you have done for regression. There's like almost no difference there, except for the resizing. Remember that the images are currently Rubik's cubes, and you need to make them into a vector of 3072 so that they fit into the neural network, okay? Not sure why this is taking so long. All right, I'm going to let it, so I'm going to write the code here. Okay, now comes the training process. Training process. Okay, and it did finish, so let me do data loader real quick. Okay, and then architecture. All right, architecture is loaded. This, doesn't matter. Leave it there. Okay. So now training process, you should be able to do on your own and complete this exercise. We've created data loader. Let's do model FN just so that it's easy to change the architecture. So I'm going to create this variable model FN, and I'm going to map to it whatever the architecture is. So in this case, it's going to be model MLP. Okay. That's done. Let's define the few parameters. How many epochs do we want? So I'm going to do n epochs equal 100. Learning rate equal 0.001. The optimizer is gonna be from optim atom, which is like stochastic gradient descent, but this is a better one. Now the algorithm is not different. Okay, it's more like optimizations and very nice parameters coding, but it's the same stochastic gradient descent that was invented by groups like Jeffrey Hinton's group and such. All right, then we provide model FN dot parameters. Remember, these are the what? The weights and the biases of the neural net. And then LR, which is the learning rate, can also be assigned. Questions? And once we do this, we are ready to build a for loop. So I'm just going to do for epoch in range and epochs. So that's 100. Then we use data loader, right? So we've done this before already, IMG's labels. Remember, we're going to read 32 images and labels at the same time. But data loader takes care of all of that. What did we call data loader? Train loader? Yep. Train loader? Okay. And then in here, what do we need to do? We basically need to grab the batch size. I made the mistake of hard coding this the other day, and then I spent like 20 minutes debugging this error. So don't make this mistake. Never hard code, right? Instead, just take batch size equal and assign to it from IMGs dot shape the zero index. Why the zero index? It gives you the number of rows. Therefore, it gives you the number of samples in your batch, which should be 32. But remember, the last batch, if it's not a multiple of 32, will not be of size 32. So do not hard code this, just get it from here. All right, so now that you have this, remember, you have to resize the images, right? How do we do it? IMGs resized equal images dot view, right? We just learned that. And then now you guys tell me. The batch size is 32 by 3 by 32 by 32, correct? I think the batch size was 32. I can't remember, but it's 32 by 3 by 32 by 32. We need to spaghettify these. So what does that mean? What should the output be? The tensor. Speak in numbers. So if it's 32 by 3 by 32 by 32, now it should be what? Huh? What is 98,304? Why? Yes. Spaghettify every image, right? I like that language, right? So 3 by 32 by 32 should be spaghettified into what? 3072. Why? The architecture expects inputs of 3072 currently, so that we don't lose any data. All right, so we're going to go ahead and do that. And we learned that if we don't hard code 32, I'm doing it again. Instead, put in batch size, comma. So it's basically the 32 and then the other 3 by 32 by 32, it can just figure it out. It's smart enough to do it. So just tell it, do that, please. And that's -1. So it's going to take those 3 dimensions and make them into 1, which will result in 3072. Got it? And that's it. After that is basically how we did it in regression. We just predict. So outputs equal model FN, which takes in images resized, right? You guys see that? And then now we need to calculate the loss, right? Remember that? We need loss FN, which is going to take what? Outputs, comma, labels. Oops. Now the labels, remember, are just 3, 7, 5. The outputs are vectors of size 10. But remember, then what do? We either take labels and one-hot encode them and use the equation, or we find a function that takes a vector here and takes a number here, and then just kind of figures out the rest. So we need to define a loss function. And so we should probably do that here. Loss FN. And we can use NN dot cross entropy loss. Got it? Now I selected this one. There's cross entropy binary. There's multi-class cross entropy. I leave it to you guys. Research these from PyTorch and kind of get a feel for the parameters that they take. Basically, the question to answer is, are they multi-class? Which they should be. And then do they take one integer for the real label and a vector for the predicted? Got it? That's an easy thing to do. Play with it. I'm pretty sure this there's a 20% chance this will give us trouble in the future, but you guys find the appropriate loss, okay? The architecture already does the softmax. So the neural net produces already softmax vectors of 10. That vector of 10 already softmax would go into loss FN, cross entropy. But also remember that labels, if this is an image, a Rubik's Cube, this is just 7 or 3. But that, in theory, should be converted to a vector of size 10. However, since we want to take advantage of functions, the functions already know that that has to happen. And so they just do it for you, if you select the right function. If you wrote the equation in here, then obviously you would have to do it. Got it? A function is just code, right? So it can convert things as part of its code. Does this make sense, guys? All right. We're at 7:50. Let me just give you all the code, and then you guys can run it. So let's, and you know how to do this already. The last part of it is what? Optimizer dot zero grad. We've already done this, right? You remember what this was for? We would zero out the gradients so they don't accumulate. That's just a quirky thing of Torch. Then we do loss dot backward, which is basically take the derivatives, and then we do optimizer step, which is basically updating the weights. And that's it. After that, every epoch, we can print out the loss, and in theory, the loss should go down. Got it? Guys, this is what we did before in regression. Notice how it's exactly the same thing. All right, so cross your fingers. I'm going to run this. And as you will see, it's going to be very slow. Why? 3072 is pretty big. And then it's one hidden layer of 200. That's a lot of weights to produce the 10 classes. You see that? Make sense? All right, so we'll stop here for today. Run it, play with it. I got a loss. Okay, all right, so it's kind of going. Good. What should happen to that loss? It should go down, right? That's the whole idea. Now, it may not go down. That's the other problem. Why? Because this is hard. CIFAR10 is more challenging than other data sets because it's color images. And think about it. You're trying to say, is this a car, a bird, a dog, a cat? That's not as easy as, is it a 7 or a 3? Oh, it's actually running kind of not too bad, right? Great. So yeah, we'll stop here for today. The code works. We will pick up here next week. Let you know, at home, let it run all the way to the end, and please report next class if the loss went down. Okay? Got it? All right, and then this kind of motivates that we need a better neural network, one that's more powerful and also that it is faster, right? And so that will lead us into CNNs. All right, guys. So let's stop the recording, and I'll see you guys next week.